Hi everyone, good day. Welcome back to our next video. In this video, we will discuss about the phases of compiler. Let us first understand what is a compiler and then we will move on to the phases of compiler. Programming languages are notations for describing computation to people and to machines. But the program written by people has to be translated into a form in which it can be executed by a computer. The system software that does these translations are called translators. Say for example, compiler, interpreter. So what is a compiler? The compiler is a program that can read a program in one language, that is the source language, say for example a C programming language, and translate it into an equivalent program in another language which we call as the machine code. The compiler during this translation process, if it detects any errors, it reports. So this is the compiler. Next, we will see what are the different phases of the compiler which it undergoes during the translation from source language to machine code. The compiler maps the source program into a semantically equivalent target program. The mapping constitutes of two major parts, analysis part and synthesis part. In analysis part, it breaks up the source program into constituent pieces and imposes a grammatical structure on them. This structure is used to create an intermediate representation of the source program. Analysis part detects the syntax and semantic error and provide error message to take corrective action. Analysis part also collects information about the source program and stores it in a data structure called a symbol table. The symbol table, an intermediate representation, is passed to the synthesis part. Analysis part is called the front end of the compiler. The analysis part is from the lexical analyzer to the intermediate code generator. Next is the synthesis part. It constructs the desired target program from the intermediate representation and the information in the symbol table. Synthesis part is called the backend. The compilation process operates as a sequence of phases, each of which transforms one representation of a source program to another. The various phases of a compiler are lexical analyzer, syntax analyzer, semantic analyzer, intermediate code generator, code optimizer, and the target program generator. Let us discuss each phase of the compiler with an example. We will see how a simple C statement is converted into the machine code. The first phase of the compiler is the lexical analyzer. It is also called as scanning. It reads the stream of characters from the source program and groups into meaningful sequences called lexemes. For each lexeme, it produces a token as output. The format for the token is token name followed by the attribute value. Token name is an abstract symbol that is used during syntax analysis. Attribute value, it refers to the entry in the symbol table for the particular token. Say for example, the statement C is equal to A plus B into 60 is a source program. When given to the lexical analyzer, it reads this stream of characters and considers each lexeme. Say for example, it will take C as a lexeme. It will consider equal to as a lexeme, A as a lexeme, plus as a lexeme and so on, and produces the token for each lexeme. Say here, now we will consider C as a lexeme. The equivalent token for this lexeme would be ID, 1, where ID is an abstract symbol for identifier and 1 points to the symbol table entry position of C. Next lexeme is the equal to. So the equal to lexeme is mapped to the token equal to. Since it does not need attribute value, the second component in this token format is omitted. For notational convenience, equal to itself is used as the abstract symbol for token name. Blanks are discarded by the lexical analyzer. After lexical analysis, the statement C is equal to A plus B into 60 gets converted into a token stream as follows. ID, 1. So this is a token. Next equal to, this is another token. ID, 2 plus is the next token. ID, 3 multiplication is the next token 60 is the next token. So this is the token stream for the given source program. C is equal to A plus B into 60. This token stream will be given as the input to the next phase of the compiler, which is the syntax analyzer. Syntax analyzer is the second phase of compiler. It is also called parsing. It converts the token stream which is taken as input from the previous stage, which is the lexical analyzer, into a tree-like representation called the syntax tree or the parse tree. In syntax tree, the interior node represents an operation and the leaf node represents the arguments of the operation. Let us consider this token stream which is taken as input from the previous phase of the compiler, which is the lexical analyzer, and is converted to this corresponding syntax tree. This syntax tree depicts the grammatical structure of the token stream. As we have seen already, the interior node represents the operation. Say for this particular token stream, multiplication is an operation, id comma 360 is the argument. So that is given as a leaf node, and multiplication is given in the interior node. So on, it constructs the syntax tree. This syntax tree will be given as input to the next phase of the compiler, which is the semantic analyzer. This phase of the compiler is the semantic analyzer. It uses the syntax tree and the information in the symbol table to check the source program for semantic consistency with the language definition. It gathers type information and saves it in either the syntax tree or the symbol table. The important part of the semantic analysis is type checking. That is, the compiler checks that each operator has matching operands. Here, the type coercion, that is implicit type conversion, is identified by the type checker and it is performed. So after doing type checking, the syntax tree is given as input to the next phase of the compiler, which is the intermediate code generation. The next phase of the compiler is the intermediate code generator. In the process of translating a source program into a target code, a compiler may construct one or more intermediate representations like syntax tree and tree address code. We already saw about syntax tree during the syntax analyzer and semantic analyzer phase. Here we'll see about the tree address code. The tree address code is an intermediate form which consists of a sequence of assembly-like instructions with 3 operands per instruction. The syntax tree from the semantic analyzer is converted into a 3 address code by the intermediate code generator as follows. T1 is equal to into float of 60, ID3 into T1, which is assigned to T2, then ID2 plus T2, which is assigned to T3. Finally, T3 is assigned to ID1. So this is the intermediate representation in the form of a 3 address code. The intermediate representation has 2 properties, easy to produce and easy to translate into the target machine code. So this 3 address code will be given as input to the next phase of the compiler, which is the code optimizer. The next phase of the compiler is the code optimizer. This phase attempts to improve the intermediate code so that better target code will result. Better means you will get a faster code, shorter code, code that consumes less power. There is a great variation in the amount of code optimization different compilers perform. Let us see how the intermediate code, which is the 3 address code from the previous stage, get optimized in this phase. T1 is equal to ID3 into 60. ID1 is equal to ID2 plus T1. So the entire set of 3 address code is returned in 2 lines. So earlier we had 4 lines. Now it is returned in 2 lines. So the above code is a shorter sequence of the intermediate code generated. So this is how it is optimized here in this phase. The last phase of the compiler is the code generator. This phase takes as input an intermediate representation of the source program and maps it into the target language. Intermediate instructions are translated into sequence of machine instructions. Code generation also selects registers, memory locations for each of the variables used by the program. The intermediate code from the code optimization phase gets converted into the machine code as follows. LDF R2, ID3, where LDF is the operation to be performed on the operands R2 and ID3. What happens here is, this is a load instruction F stands for floating point values. So we are working with floating point values. So it is LDF. So whatever is there in ID3 will be transferred to the register R2. The next instruction is MULF, which means multiplication operation. Working with floating point values. So we have F. It multiplies the value 60, the value in the register R2, and stores the result back in the register R2. The next instruction is LDF R1, ID2, where LDF is the operation, load operation. Here again, the value in the variable ID2 will be transferred to the register R1. So next instruction is performing add operation, add F. So here it will add the content of R1 and R2 and store the result back in R1. So finally we have the store instruction where the content of R1 is stored back to the variable ID1. So this is the target machine code which will be understood by the machine. So we understood the various phases of compiler, how a C statement is converted into a target machine code. In this video, we discussed about the various phases of the compiler. Hope this video was useful to you. Kindly like, share and subscribe. Thank you.